And we have 4 more weeks left. The agenda is today will be the last that we're going to look at shearing stress, and we're going to do longitudinal shear on beam section. Test 2 correction will be held on 6th of July, which is on Thursday, 7 p.m. to 9:30 p.m. And it will be, the location is BSB, Burp Science Building, room 105. And because of the correction, there will be no lecture on July 6th. Okay. So, and the correction list is on Avenue to Learn. So you have your student number, you have to do correction. You'll see your student number and what question you have to correct. Okay. So today we are going to, as I said, it's the last section on shearing stress. And we are going to analyze the strength of joints in shear loading conditions. The thing we like to emphasize over here is the strength of joints. Okay, we are going to look at the joints. Okay, so if you were to go onto Avenue to Learn, I posted quite a bit of examples that we'll be using today. So you can go and download. Okay, so if we look at the structure over here, okay, so just one of the question. If we look at the structure over here, so if I were to draw our transformation first, so this is our X, Y, and this is rotation Z. And over here, this is our cross-sectional view. So if I were to draw the transformation on this side, this will be Y, this will be Z, and this will be rotation by X. And where our structure will fail, okay, is going to fail first at the joints that I'm going to draw in red. Okay, so this will be, or before I go on, let's look at this structure. So you have 4 members over here, 4 individual separate member. Okay, so you have member number 1, you have member number 2, and you have a member number 3, and you have member number 4. And all 4 members are held together by a fastener. So this is the fastener over here that I'm going to draw in blue. Okay, so these are the fastener. This is also the fastener. So they're held together by the fastener. So where this structure will fail, the structure will fail at the joints. Okay, the joints are the weakest. So I'm highlighting the joints. This is where it is the weakest. Okay, so these are the joints. Okay, so failure. So highlight in red. These are the joints. And failure will always occur at the joints first. Okay, it's like where it's like us human, right? Where we are weakest is our knees, our elbows, right? The knee usually is a problem part, right? So that's where you have knee replacement. That's where we have hip replacement. Okay, so because it's the weakest part. So the formula that we're going to use on this, okay, there's a new formula. So the shear stress formula that we're going to use is still the same. Okay, so this is VQ over IT. And the next formula we're going to use, which is the shear for Q, is equal to VQ over I. And we know the units over here is Newton meter cube over meter 4. Okay, so it's Newton per meter. And Q over here is also, there's another formula that I have to introduce you on this topic over here, where you have Q is equal to fastener resistance force divided by fastener spacing. Okay, so this unit is also Newton over meter. Okay, so this is something new that we've not seen before. Okay, that we are going to use for longitudinal shear is fastener resistance force over fastener spacing. Okay, and there are two rules that I want you all to remember. Okay, so two rules that have to be used. Okay, on top of the 5 that I've written down. Okay, so for longitudinal shear, right? For longitudinal shear, must add 2 more rules. So what are the rules to add? So the first rule, okay, is the member must distribute, must entirely distribute the shearing stress so this is one, and the next one is the joints or fastener is to transmit the shearing stress or shear flow from one member to the other. So what do we mean by that? Okay, what do we mean by these two terms over here? Okay, so I'm going to take this cross section again. Okay, so now we know that there's a shear force coming from the top, B. Okay, we know that. Okay, so now I'm going to draw. Okay, I'm going to draw the top portion. Okay, I'm just going to draw the top portion to explain what do I mean by those two rules. Okay, so we know that this is about over here. This is the centroid. Okay. So I'm going to draw member number 1 first. Okay, I'm going to draw a bigger view of member number 1. Okay, so this is member number 1, which is corresponding to this member number 1. Okay, so this is member number 1. Okay. So when you have a ply load over here, V, right? The shear flow will flow towards, will transmit. Okay, the word to use is will distribute. Sorry, will distribute first. So this will, the member must distribute the entire shear. So what do you mean by distribute? Is you have the shear moving, the shear flow moving down this way. Okay, so this is shear flow. So only after the entire structure has been distributed on the shear flow, the fastener is then used to transmit. Okay, so I'm going to draw the fastener next. Okay, so this is the fastener. So I'm going to sketch the fastener. Okay, so this is our, I will use a different color, I do apologize. So this is the fastener. Okay, so only after it completely distribute. Okay, so shear flow completely distribute in the entire member number 1. Okay, then the fastener will transmit. So I'm going to draw a different arrow now. Okay, it will transmit the wrong thickness. It will transmit the shear flow. Okay, transmit the shear flow or the shear stress. So this one over here is to transmit. Okay, over here, this is to transmit the fastener will transmit the shear flow to another member. Okay. Then after transmitting, then it will go to the vertical web. So I'm going to sketch the vertical web separately. One color. Okay, so this is our vertical web. Okay, so this is our vertical web. Okay, then we'll transmit onto the member number. Okay, so this is our member. What did we write earlier? Member 4 and member 3. Okay, member 3, member 4. Then it will transmit the shear flow, okay, into the vertical member. Okay. So you ask me, Eugene, why this is important? Okay. So this is important is because only you can visualize it this way, then you are able to calculate the what? the first moment of area. The most difficult thing to calculate in any of this equation is your what? And we know this by now, is the first moment of area. Okay, that is the most confusing part. Okay, so that's why you have to understand this concept first. Okay, so rather me talking any further, let's do an example, and this example is a very good open-ended question. I'll emphasize again, this is a really good open-ended. This is like a real engineering problem. Okay, so I want you to look into this problem now, which I'm going to get on our last page. Okay, example number 1.